Dear students, today's topic of my lecture, Units and Measurement, Chapter 2, Part 2. So what you have to learn in this chapter that you see here, first we have to discuss definitions of fundamental units, then practical units for measuring small distances, after that practical units for measuring large distances, then practical unit used for measuring large masses, then practical unit used for measuring small masses, then practical units used for measuring very small masses, then practical units used for measuring small time, then practical units used for measuring bigger time. So one by one I explain each and everything. So first you see the definition of fundamental SI units. The first is meter. So what is 1 meter? The meter is the length of the path traveled by light in vacuum during a time interval of 1 upon 299,792,458 of a second, and this definition was given in 1983. Second unit is kilogram. Kilogram is equal to the mass of international prototype of the kilogram, a platinum iridium alloy cylinder which is kept at International Bureau of Weights and Measures near Paris, France, and this definition was given in 1889. Means a platinum iridium alloy cylinder was kept in International Bureau of Weights and Measures, that is in France, and this cylinder is of 1 kg, and that definition is known as 1 kilogram, and that mass of that platinum iridium cylinder basically is equal to the 1 kilogram. But now this definition has been changed. Now in place of the kilogram we have to use kibble. Now the second is the duration of 9192631770 periods of the radiations. They are the microwave radiations corresponding to the transition between two hyperfine labels of the ground state of cesium-133 atom, and this definition was given in 1967. So all these three definitions I will explain you today in detail also. Now next is ampere. Ampere is that constant current if maintained in two state parallel current carrying conductors of infinite length of negligible circular cross section and placed at 1 meter distance apart in vacuum, then there is a force which acts is equal to 2 into 10 is power minus 7 Newton per meter of length, and this definition was given in 1948. And in class 12 you have to perform a derivation for calculating this force between the two current carrying infinite length conductors, and from there we get this definition, and that formula of the force that comes F upon L equal to mu naught upon 4 pi 2 I1 I2 upon R. So by this formula we have to define the definition of 1 ampere, and which comes the same as written over to here. Now Kelvin. The Kelvin is the fraction 1 upon 273.16 of thermodynamic temperature of the triple point of water, and this definition was given in 1967. Then candela. The candela is the luminous intensity in a given direction of source that emits monochromatic radiations of frequency 540 into 10 to the power 12 Hz, and that has a radiant intensity in that direction of 1 upon 683 watt per stadian, and that definition came in 1979. And the seventh fundamental unit definition, that is mole. The mole is the amount of substance of a system which contains as many elementary entities as there are atoms in 0.012 kilogram of carbon 12, and this definition was given in 1971. So these are the seven fundamental units and their definitions. Now we have to use the two supplementary units. There is radian and steradian, and these supplementary physical quantities are plane angle and solid angle. So you see the definition of these two supplementary units. Plane angle is basically defined as the ratio of r to the radius, and it is defined by the simple concept of the angle, that is angle equal to arc upon radius and measured in radian. So you can see here, this is the r which we are representing by L, and r is the radius and d theta is the angle, that is plane angle. Now if we are saying that it is a d theta, then you see that this one is small arc, say dl. So then d theta equal to dl upon r, and theta equal to L upon r. So this is called plane angle, and unit of plane angle is radian. Similarly, we can define the solid angle. Solid angle d omega is the ratio of intercepted area dA. You can see here, of a spherical surface described at the apex O, which is at center, to square of its radius. Radius is r, and its SI unit is steradian. So from here it is very clear, d omega equal to dA upon r square. That is called solid angle. So this is about plane angle and solid angle. Now come to the another topic, that is SI unit of length, which is meter, that we have to discuss here in detail. In 1960, an atomic standard for the meter was established using the wavelength of orange red light emitted by excited atom of krypton 3686 from this length standard. Then the speed of light in vacuum was measured to be 299,792,458 meter per second. But the value which we are getting of 1 meter is not so precise. So that's why in 1983 this definition is modified, which will give you more precise value, and that definition of length was changed in November 1993, that the speed of light in vacuum was defined to be precisely 299,792,458 meter per second. Thus, the new definition of the meter is the length of path traveled by the light in vacuum during a time interval of 1 upon 299,792,458 second, and that you can see here in a figure. Here we are taking a light source, from it the light wave travels, and after the 1 second it travels the distance 299,792,458 meter. And this modern definition provides a much more precise standard of length than the one based on a wavelength of light. So this is about SI unit of length, that is meter. Now we can see some practical units of length. That is, the first one is practical unit for measuring small distances. So first one is Fermi. Fermi is a small practical unit of distance used to measure nuclear sizes. It is also called femtometer. So 1 Fermi equal to 10 is power minus 15 meter. Some more practical units for measuring small distances, and they are angstrom. It is used to express the wavelength of light. So 1 angstrom equal to 10 is power minus 10 meter. Nanometer. It is also used to express wavelength of light. That is 1 nanometer equal to 10 is power minus 9 meter. And then micron, it is the unit of distance defined in micrometer. So 1 micron equal to 1 micrometer equal to 10 is power minus 6 meter. Millimeter, it is the unit of small distance. So 1 millimeter equal to 10 is power minus 3 meter. Similarly, centimeter, it is also the unit of small distance. So 1 centimeter equal to 10 is power minus 2 meter. And 1 micrometer 10 is power minus 6 meter. 1 nanometer 10 is power minus 9 meter. 1 angstrom 10 is power minus 10 meter. 1 Fermi 10 is power minus 15 meter. So these are the some practical units for measuring small distances. Similarly, we can also find out the practical units for measuring the large distances. The first one is light year. As its name indicates, light year. So it is not the unit of time, it is the unit of large distance. So light year is the distance traveled by light in 1 year in vacuum. So we have to use the formula speed equal to distance upon time, and distance equal to speed into time. So 1 light year distance is equal to speed of light multiplied by time of 1 year. And the speed of light that we know, 3 into 10 is power 8 meter per second, and time 365.25 days multiplied by 24 hours, 60 minutes, then 60 seconds. So this is 1 year calculation in second. After calculating, you will get 1 light year equal to 9.467 into 10 is power 15 meter. Similarly, another unit is astronomical unit. Astronomical unit is the average distance of the center of the sun from the center of the earth. So that is 1 astronomical unit equal to 1.496 into 10 is power 11 meter. Similarly, another unit is parsec, which is known as parallactic second. So it is again a unit of distance. So parsec is the distance at which an arc of length 1 astronomical unit subtend an angle of 1 second of that arc. So you can see here in the diagram, the average distance between the center of the sun to the center of the earth is 1 astronomical unit, which subtend an angle of 1 second. Here it is a star. Then the distance between the sun and the star, that is in parsec, which is represented by d. So we calculate it by the simple definition of angle, that is angle equal to arc upon radius. So angle is 1 second. It is the representation of 1 second, which is equal to 1 astronomical unit upon 1 parsec. Or you can say that parsec, 1 parsec multiplied by 1 second equal to 1 astronomical unit. But our purpose to calculate 1 parsec. So we have to apply this formula. So 1 parsec equal to 1 astronomical unit is 1.496 into 10 is power 11 meter upon 1 second. 1 second that you have to convert in radian. So 1 upon 60 into 60, that is 3600 multiplied pi upon 180. So this is the conversion of 1 second angle into radian. So when you solve it, you will get 1 parsec equal to 3.08 into 10 is power 16 meter. Now we find out the relation between parsec and light year. That we know that 1 light year equal to 9.46 into 10 is power 15 meter, and 1 parsec equal to 3.08 into 10 is power 16 meter. We divide it, 1 parsec upon 1 light year equal to 3.08 into 10 is power 16 divided by 9.46 into 10 is power 15, and when you solve it you will get 1 parsec equal to 3.26 light year. So you remember this conversion and this relation also. Now relation between astronomical unit and light year. So as we know that 1 light year equal to 9.46 into 10 is power 15 meter, and 1 astronomical unit equal to 1.496 into 10 is power 11 meter. Then 1 astronomical unit upon 1 light year equal to 1.496 into 10 is power 11 upon 9.46 into 10 is power 15, or 1 light year upon 1 astronomical unit equal to 9.46 into 10 is power 15 upon 1.496 into 10 is power 11. So when you solve it, you will get 1 light year equal to 6.3 into 10 is power 4 astronomical unit. So this is the relation between astronomical unit and light year. Now the SI unit of mass is kilogram. You can see here in little detail. So kilogram is equal to the mass of international prototype of kilogram. That is the mass of a platinum iridium alloy cylinder, which is kept at International Bureau of Weights and Measure at Sivers near Paris, France. So you see that here, this is a cylinder which is kept here, and it is kept at International Bureau of Weights and Measure in France, and this cylinder is basically a platinum iridium alloy whose mass is 1 kg. Now the definition of kilogram has been changed. Now it is kibble. So now it is now defined in kibble. Now practical units of measuring large masses, that is 1 ton or 1 metric ton equal to 1000 kg. Similarly 1 quintal equal to 100 kg. 1 slug equal to 14.57 kg. 1 pound is 0.4536 kg, and 1 Chandrasekhar limit, that is 1 CSL equal to 1.4 times the mass of the sun, and this CSL is the largest practical unit of mass that we have to use in astronomy. Now practical unit used for measuring small masses, that is 1 gram equal to 10 is power minus 3 kg. Similarly, 1 milligram equal to 10 is power minus 6 kg. That is 1 milligram equal to 10 is power minus 3 gram. Now practical unit used for measuring very small masses, that is atomic mass unit. So atomic mass unit we have to define is a unit in which the mass of atomic particles such as proton, neutron and electron is expressed, and it is also called unified atomic mass unit, and it is represented by a symbol small u. So it is defined as 1/12 of the mass of one carbon 12 atom. So the mass of 6.02 into 10 is power 23 atoms of carbon 12 consists 12 kg. So from here, by the unitary method, you can say that 1 AMU or U equal to 1 upon 12 into 12 upon 6.02 into 10 is power 23 gram. When you solve it, you will get 1.66 into 10 is power minus 23 kg, or 1.66 into 10 is power minus 27 kg, because we have to use SI units. Now the unit of time is second. So earlier, up to 1967, that is from 1889 until 1967, the unit of time was defined as a certain fraction of mean solar day, the average time between successive arrivals of the sun at its highest point in the sky. But that method is not giving the value very precisely, so that's why the present system that which we are using, that is adopted in 1967, is much more precise and based on atomic clock, which uses energy differences between the two lowest energy states of the cesium atom. When bombarded by the microwaves of precisely the proper frequency, then cesium atoms undergo a transition from one of these states to the other. You can see here in the diagram that microwave radiations with frequency exactly 9192631770 cycle per second, when fall onto the cesium 133 atom, then you see that before these radiations fall on cesium 133 atom, the motion of electrons in its orbit is anti-clockwise. You can see here. But when these microwave radiations with frequency exactly 9192631770 cycle per second falls on cesium 133 atom, then it reverses the spin of electron. Means now the electron starts revolving in clockwise direction, and this process takes place within 1 second. So that's why the time taken to convert this spin, when microwave radiations with frequency exactly 9192631770 cycles incident on it, is known as 1 second time. So that's why we say that an atomic clock uses this phenomena to tune microwave to this exact frequency. It then counts 1 second for each 9192631770 cycles of the radiation. That's why the definition becomes 1 second is the duration of 9192631770 periods of microwave radiation corresponding to the transition between the two hyperfine levels of the ground state of the cesium 133 atom. So this is about the unit of time, that is second. Now we take some practical units used for measuring the smaller time, that is 1 millisecond equal to 10 to the power minus 3 second, 1 microsecond equal to 10 to the power minus 6 second, 1 shake equal to 10 to the power minus 8 second, 1 nanosecond equal to 10 to the power minus 9 second, and their symbolical representation is also given here. Now similarly, practical units used for measuring the bigger time, and they are here, means 1 minute, it is the time of duration of 60 second, that is 1 minute equal to 60 second. 1 hour, it is the time of duration of 60 minutes, so 1 hour equal to 60 minutes. If you convert into the second, then 60 into 60, that is 1 hour equal to 3600 second, that is 3600 second. Solar day, it is the time taken by Earth to complete one rotation about its own axis with respect to Sun. So one day basically equal to 24 hours, which is equal to 24 into 60 minutes. So 1440 minutes, convert into second, then 24 into 60 into 60. So in one day you have the 86,400 seconds. So as we say that we don't have the time, but in one day we have 86,400 seconds. Solar year, it is the time taken by Earth to complete one revolution around the Sun in its orbit. So one solar year equal to 365.25 average solar days. There are some more units which are here. You can see tropical year. It is defined as the year in which the total solar eclipse takes place. Next one is leap year, the year which is divisible by 4 and in which month of February is 29 days. That is one leap year equal to 366 days. Lunar month, it is the time taken by moon to complete one revolution around the earth in its orbit. Our Hindu, Vikram and Shak, and Muslim Hijri calendars are based on phases of moon as seen from our earth. So one lunar month equal to 27.3 days. Decade, a decade is equal to 10 years. A decade is equal to 10 years. That is one decade equal to 10 years, which is equal to 3.1536 into 10 to the power 8 second. Century, a century is equal to 100 years. In a century, there will be 24 years, each of 366 days, and 76 years, each of 365 days. Thus, one century equal to 100 years, and we calculate 24 into 366 plus 76 into 365 days. So after calculation, it comes 36,524 days and 3.16 into 10 to the power 9 seconds. Millennium, a millennium is equal to 1000 years. So 1 millennium equal to 3.16 into 10 to the power 10 seconds. So this is about practical units of measuring smaller and bigger time. So if you like my video, like it, subscribe, press the bell icon, stay safe, stay healthy, learn physics by staying at home through my YouTube channel. Thank you and have a nice day.